All right, so we got some warm-up problems here. It says identify as even, odd, identify the function type, and identify the domain. They're letters A, B, C because they're in order and they kind of look like it. All right, so I would start with this. I look at letter A, and I see x squared plus 2. I know that's a polynomial. I know 1 over x squared is a reciprocal or rational. So everybody, the type of function here is where I'll start. That's composite. Does everybody agree? This is a composite function. If I ask you to name the parts, I would accept a couple answers. Poly and rational is probably what I would call it. Okay? I would accept polynomial and reciprocal. Okay? I would actually accept a polynomial and a power function. Because you remember yesterday we talked about the power function could have a negative exponent on it. We can talk about it any number of ways. I'll take all of them. The harder part here, before I do whether it's even or odd, is the domain. I know the domain of this is all reals. I know the domain of this is all reals except 0. What's the limiting factor? Is the reciprocal portion or the rational portion? So the domain of this function is all reals except x can't be 0. All right. When I ask even, odd, everybody, it's even, odd, or neither, okay? It's even, odd, or neither. Now, in this case, I will tell you right now, I see 3 powers. I see positive 2, I see negative 2, and I see 0. So everybody, I know this function's even. This is an even function. I'm going to prove it, because if I said justify, the horrible J word, justify, you'd have to justify. You justify, I'll do it in green, by plugging in negative x. And remember, I need to see enough steps to believe that you understand what you're doing. We don't just don't make it appear Clayton Hale at the bottom of the page. You didn't say this. Yeah, that was funny last year. This year, this is it. You got to show that you get there. And this proves it's an even function in green. I didn't ask you to prove it on this warm-up. It is even. And I can't stress enough. These 3 things. 1, 2, 3. And this is the justification of the even. All right? All right, letter B. G of x equals x cubed minus x. Everybody, this is a polynomial. This is a polynomial function. When it's a polynomial, I don't have to think about domain. Domain will always be all real polynomials. Boom. Done. Polynomial, all real. Domain and polynomials are tied together just like that. Now I look at the powers, 3 and 1. I know right now this is odd. Now I'll prove it in blue. I substitute negative x. And I get negative x plus x. Negative x cubed plus x, I'm sorry. I know that this is not the same as the function. I look here and the sign's different. So I think to myself, all right, I need to pull out the negative and see if it's the same. When I do that, it is. So this is negative g of x, which means that it is odd. And I just justified that this is odd. Okay? That mirrors it from first to third about the origin, right? Even is across the y-axis. Everybody, sine x. Can we all read the trig function? It is all reals. And hopefully, in your head, you are picturing something that goes from -1 to 1, like this. And we know that a sine function goes through the origin. I can tell immediately right now that it is not even if we think of this graph. Because an even would look like this, right? It'd be rolling hills, like a first grader making hills, all right, in an art class. It is not that. If I rotate this, does it come back here? The answer is yes. So from the graph, we can tell that this function is odd. But now we want to justify it. I didn't ask you to do that for the warm-up. I'm going to justify it. So I have to substitute what? Negative x. All right. Judah, we have to think about what this looks like in the first and fourth quadrant. Albany, Kyle, I don't know if you guys thought about it this way last year. All right. If you rotate a triangle x here, you go x degrees in the first quadrant. All right. You guys all agree the sine of this triangle would be the height. The opposite over the hypotenuse, right? Be over the h of that triangle. What if I go into the fourth quadrant and I go down negative x? What's the only difference between the O and the h of the red triangle versus the O and the h of the blue triangle? O is negative. So there's a rule. Remember, we learned last year in pre-calculus about this. When the argument is negative in a sine function, you can drop it. It has an equivalent value, which is written this way. Oh, look at that. And everybody, h of x is sine x, so negative sine x. So this is negative h of x. And is that an odd? That is an odd. Thus odd, QED. As long as we're talking about this before I turn on the video, let's talk about cosine of these two triangles. I use purple. And I put the A here. AH both positive. So what do we know about cosine negative x? It's even because cosine negative x is equal to cos x. So everybody, if I graph a cosine function, there's the curve for cosine on the right side of the origin. Here's the curve on the left side. Do you see how they mirror across the y-axis? So this is an even function. So cosine is even, sine is odd. It helps to memorize that, everybody. It helps to have that memorized. It's always that on the parent function. If you start shifting things left and right, you put a phase shift in, amplitude-wise, does that change anything? No. But if you put a phase shift in, a compression is okay, a stretch is okay, but phase shifts and shifts vertically change everything. On the odd, sure. On the even, the vertical shift doesn't change. Oh, you're talking value. I'm talking the angle. Look here, I'm talking about going counterclockwise here at cosine negative x. That's going down in the fourth quadrant versus cosine x going up. Not the value. You're right. A negative ratio would put a negative ratio for cosine, right, would be quadrant 2 or quadrant 3, because that would be the x value. Yes.